Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Numerical Solutions for Systems of Linear Equations, and it is going to introduce direct methods and iterative solvers for systems of linear equations. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the direct methods and iterative solvers before wrapping up with conclusions. Now we study numerical methods to solve a system of linear equations. Here is the problem that we have n unknowns and we have n linear equations. In the general form, we can write it as following. Since each equation is linear in our unknown, we will solve our unknown to be x1, x2, and all the way to xn, and each is multiplied by some coefficients. We label it with a double index a11, a12, a1n, and that is for equation 1. And then you have equation 2, where you change the first index into 2. So a21, a22, and so on, and then all the way down to the end equation. If the coefficients ij's are nice in certain sense, then the system has a unique solution. Now we write it into a matrix vector form. We think the unknowns x. We set them up into a column vector, and we call it x vector. And the right hand side b, we do the same thing. We form a vector b. Then the system can be written as a matrix A times x equals to b, where A is a n by n square matrix. Its coefficients are exactly the coefficients in front of the axis in the system here. We prepared in the corresponding position. We shall be familiar with this procedure called Gaussian elimination. Through row operation, we can do the following. The goal is to make an upper triangular system. Here is the algorithm. First, we need a for loop to go through all the columns from column 1 to column n-1. That means take care of each column in each of the I. And then for each I, we have to go through equation j plus 1, j plus 2, all the way to equation number n. Therefore, we have the second for loop to do that. For each I, we'll have to take equation m, multiply by suitable constant aij over ajj, and then subtract it from equation j to make that 0. And then we replace that for equation j, and you end your two loops. Note that here, actually the I and the j are indicating the whole equation. There are actually many terms in the equation. There is hidden for loop in this line here. This step is called forward elimination. After the forward elimination, we end up with an upper triangular system, so we can start to solve it. Starting from the last equation here, we can solve this and get xn, and plug that back into the previous equation for xn-1. We can keep going up all the way to equation 1 for all the x's. This step is called backward substitution. Let's put this into an algorithm form. What do you have to do first? Initialize, compute an xn, and then you go through equation m-1, m-2, all the way to 1. For each of these I, you keep the xi on the left hand side and move everything else to the right hand side, because you already know all these xj's, and then you compute it. This is a naive Gaussian elimination. The order in which equations are written can be important to achieve an accurate computation. In this video, we also introduce Gaussian elimination with scaled partial pivoting. The main idea in this pivoting process is to use for I equation the max absolute aik over si for aii, where si is a scaling factor for equation number I. To simplify the algorithm, the scaling factor is computed only once at the beginning of the algorithm, and is not updated later. This is a very effective algorithm and yet cheap to compute. The algorithm will be shown as follows. Firstly, we compute a scaling vector S and keep this vector S for the rest of the computation. The second, we will find the index k for each I, and exchange equation k and 1, and do one step of the Gaussian elimination algorithm. Repeat the second step for the remaining system, and continue through all columns. Note that Si is unchanged, and is always associated with the original number I for the equation. Now we can use a simple example to see the two methods. We want to solve this linear system. Note that the coefficient matrix here is a Van Helmont matrix, and we know the exact solution as shown in here. We use the naive Gaussian elimination and the Gaussian elimination with pivoting to compute the system, and obtain the following results. We see the round-off errors are magnitude by a huge factor in the solution. The max error using the naive Gaussian elimination is much larger than the one using pivoting. However, in a system of Ax equal to b, if the matrix A is large, solving the system using Gaussian elimination requires a long time. Faster methods are needed. We now look at fixed point iteration methods to find approximate solutions to linear systems, and we'll be considering the following problem. We want to find the approximate solution to the system Ax equal to b, and in particular, the A matrix has the following properties. First, it is a large system meaning, and is very big, you can say, and equals to 1 million for example, and also a matrix has a small percent of non-zero elements, so most of the elements in A are zero, and this is called a sparse matrix. And finally, very often, but not necessarily, it could be structured, meaning that we know exactly where the non-zeros are and what they are. It has a clear structure, and this type of matrix will come very often in the discretization of numerical methods for differential equations, for example. If we know it is structured, that means if I want to do the computations, A times a vector x, that step could be computed very efficiently with little time. So, the main idea now will be, instead of trying to compute an inverse, which is expensive now, we perform the cheap operation, that is the multiplication of A with a vector. Let's write out our system into n equations and n unknowns. So this is what we want to solve the problem. We have the main idea of these methods that we will be taking about more or less a kind of a fixed point iteration, but in the system setting. We will start with by rewriting the system into an equivalent. I can also write it in a compact form. For the i's equation, I will just get this expression, and where on all the other terms the summation. I put them in the sum over j equals to 1 to n of aij xj, except the point where j equals to I, and that one I left on the left hand side. This goes through for all the equations. Now we look at the Jacobi iteration. So you need to have a starting point, an initial vector x0. We use the upper index to indicate the number of iteration x0 is a vector has n components transposed. So it is a column vector, and then we go 3 iterations k equals to 0, 1, 2, all the way until stop criteria is met. And then we go through each equation I from 1 to 3 all the way to n. And then for each equation, we perform exactly this fixed point iteration algorithm, putting xk on the right hand side and compute it and return the value into xk plus 1. And then you hang your loops. So one more thing to talk about is how to choose a reasonable starting point. Then let's look at the starting vector. we can just choose some simple and vector. Let's say all vectors could be 0, and that the choice of the right-hand side vector be. I will copy that to be my initial guess, and then there is a better choice if your matrix is diagonal dominant. Since the diagonal term is very big, you can think that the left-hand side is dominated by the diagonal, and then you throw away the rest, and then you can solve a diagonal system which give you trivially this solution for each xi, and then you simply use that as your initial choice, and that is closer to the solution as your random other choices. We now look at an improvement over Jacobi iteration. Basically, this summation can be breaking up into two summations, one of those j less than I, and the other those j bigger than I, and that is exactly what we write down here. So this part is the summation j from 1 to I minus 1. We now make the following observation. If now my computation is done in a sequential way that I go through I equal to 1, 2, 3, all the way to n, then in the first summation term, all the xj values are actually already computed for step k plus 1. Now assuming that it converges, or we hope for convergence, then the value at step k plus 1 shall be a better one than the value at the step k. So we would be better off if we use those better values right away. We will replace all these xjk's with the newly computed xjk plus 1, and this is exactly the Gauss-Seidel iteration. The main idea of Gauss-Seidel iteration is to use the latest computer value for xi's. So here is the algorithm, choosing an initial guess which is the same, and then we run through the iteration until stop criteria which is the same. For each equation, now we go through it in a sequential way, and we have this iteration. This is the same as the Jacobi iteration except for this summation sign. We have a new thing here that is this k plus 1, so we are using the newly computed value. We will now take a look at a couple of examples and how they perform. In this test study, we choose a matrix to be a 6 times 6 matrix, which is listed here. Its diagonal is 4. It is kind of a sparse, has many zeros. After I all know, we have just some values -1 appearing here. We choose the right-hand side vector b to be this value. That is a column vector, and one can show or one can verify that the exact solution is 1, 2, 1, 2, 1, 2. So it becomes a bit easier for us to see if our iteration converges. We will solve this with iterative methods, Jacobian, Gauss-Seidel. All of two will be started with the same initial value, which is the so-called our smart choice. We give this broad error against the number of iterations for two methods after many iterations. So the blue line here is the Jacobi iteration, and the red one is the Gauss-Seidel. The error here is plotted in the logarithm on scale. So you see, if your error tolerance shall be 10 to the -5, which is approximately here, and you draw a horizontal line, then you see Jacobi iteration will require about 25 iterations. The Gauss-Seidel is about 12 iterations. It clearly shows that the Gauss-Seidel is faster than Jacobi. From conclusions, what we learned: Gaussian elimination, also known as row reduction, is an algorithm in linear algebra for solving a system of linear equations. In numerical linear algebra, the Gauss-Seidel method is an iterative method used to solve a system of linear equations. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.